Good morning, everybody. This is Jorge with KETIV Technologies. Joined with me is Nikhil as well. We're both here, part of KETIV. I'm a project manager for KETIV and have worked extensively with a lot of you as well, by the way, probably. And Nikhil is a little newer to our team, but has some vast experience in simulation. So looking forward here to helping you all demystifying nonlinear FEA and Nastran In-CAD. So first of all, let's demystify the title itself. The thing today here is to linear or not to linear. That is the question. So joking aside, really we want to make sure it's very clear what it means to do nonlinear. I think too often, I'm sure Nikhil can attest to this as well, and he's shaking his head yes, that a lot of times we say, well, nonlinear means that, hey, it's a nonlinear material such as plastic or rubber. But there's actually a whole lot more to that. It comes up when we're working on support cases, right? It comes up when we're talking to customers and they're running their own simulations. So we want to make sure it was really clear, or as clear as can be, because there isn't an exact value, but at least there's some information you'll want to know before deciding or realizing that you need to do one or the other. So what we'll do today is we'll make sure we cover, what is nonlinearity? What does that really mean? Why does it occur? What are some different examples or types of FEA problems that nonlinear will solve? And finally, we'll actually jump into how to set this up and what it means to do it inside of Nastran In-CAD. So take a quick step back here. I'm not sure how many folks here on the line have done FEA before, but one key thing that I like to keep in mind is most of all, it helps reduce having to either outsource or having to prototype the design you're working on. A lot of times, I'm sure some of you can attest to currently using outsourcing or going to consultants to get their stamp of approval. I'm not necessarily saying go away with it, do away with that completely. You might be able to, depending on your experience, of course, but you might also just realize, instead of having so many iterations going back and forth, I can start to get an idea of how my design's working out. So I don't have to, spend all that time or money in order to get that part done. So you can reduce those iterations either on physical prototyping, 3D printing, as well as having to send that out. Of course, with that comes a lot of other added benefits, such as improving the weight of it, the cost of the design itself, being able to be a little more innovative also up front, and doing this all within your same CAD system, right? So before we get into nonlinear, what is linear? So linear is most commonly any type of metals, usually, right? Unless it's some composite or something like that, I would say.
Those wouldn't be linear either. They're pretty much it's metals.
Okay.
For the most part.
Pretty much metals, you heard it. But it also means that there's small displacements. Now, small displacements that can vary, right? I can't give you an exact number. What I can tell you is the table we're using right now in front of us. If you put 10,000 pounds, that's a pretty large displacement. I'm exaggerating, I know, but 100 pounds, I would say that's more within the linear analysis range that we'd want to do.
Yeah, small and large are pretty relative to the size, the surface area on which the load is actually being applied. So it's always a function of the type of design and the loads that it's actually going to be under.
Exactly. Okay, there you have it, and that's linear. So what's nonlinear? Somewhat the opposite of that, right? Then we start talking about, first we'll talk about contacting parts. Think of large movements between components, such as a snap fit, like a buckle, right? You got a plastic buckle, not just because it's plastic, but really more because of the type of displacement. There's so much displacement that you really need to study what happens throughout the different time increments, perhaps. You might find where the max is, and then you do a separate load on there, but those are just a couple examples, right? Material is the most obvious one, probably, right? The nonlinear materials such as plastics or rubber. What that really means is when you go beyond the yield or the ultimate strength of the material itself. So that means if we are going beyond that with metal, then that's technically nonlinear. And maybe this is another way to explain it is, what happens is when it goes beyond its yield, it doesn't necessarily break. It just might not return to its original form. So if you have a piece of metal that you're bending, then it's no longer going to go back to straight. It's going to stay bent over, right? And then there's geometric, large deformation. That's really what I'm talking about right now, that the material itself is now going to deform, no longer go back to its original shape. And this can happen with metal as well. So once you realize that you've gone beyond that ultimate strength, and that's when you start looking at where it's really a nonlinear solution. And so that's really what I was talking about right now. The material, you want to ask yourself, are you within the linear elastic range or not? Linear, you see there on the far left, for example, once you go beyond that point, you really start to hit the nonlinear side of things. So you might have to either look up the material within your library and Inventor, or you might have to go, research, do a little more research on that material online. Usually something like MatWeb, for example, might bring that up, for example. And with plastic, you see it actually curves there at the end because, again, it doesn't actually break at the yield, right? It just starts to deform, really. And in some cases, you might want something to deform because it becomes actually stronger at that point, right, Nikhil?
Yeah. Depending on, again, the microstructure of the material and how that's been strengthened and hardened and all that stuff, it can potentially become stronger after hitting the plastic region.
Right. So the point there, the last point you see, should you be? Do you actually want to be in that range, right? So here's just a few examples. There's a lot more examples, more than this. And I was trying to find some images here, but I just wanted to make sure I stuck to the kind of general idea of what nonlinear is. So Nastran In-CAD within Inventor, within the product design suite collection, is included in there. And you'll see some asterisks here, for example, like buckling, right? Can you want to explain that just a little bit, Nikhil?
Right. So buckling in a linear sense is when you have a large load on a very small surface area. That essentially is the definition of buckling. Now, typically buckling is linear if you're looking at just a simple buckling analysis. But oftentimes you'll find that buckling just tends to be a component of the behavior of any assembly itself, because you do have small components, you do have stresses and forces that get transferred. So individual components may be buckling in an assembly. So that, again, if you were to capture that, and if that buckling was significant enough, then you might want to use a nonlinear analysis to actually capture that accurately.
Perfect. Thanks, Nikhil. So let's go ahead and get into the setup. So now Nikhil's going to go into Nastran In-CAD and show you what that looks like to actually get this up and give you some tips on when you're trying to set something up. I think he's going to go through something with linear and nonlinear, but I won't steal his thunder. I'll let him go through that.
All right. Thanks, Jorge. So some of you may have seen this this hedge trimmer before, but the part of this it would be awfully fun to try and simulate the working of this completely. But the part that we're going to focus on is the guard itself, this little guard here. So I've just changed the visibility on that a little bit to make it not clear and just so we can see it. The guard is normally made of a plastic material. So this is the obvious non-linearity that Jorge was referencing. The material we're going to be using for this is, it says ABS plastic, but I'm going to change that and try and use polycarbonate, a blend of polycarbonate and ABS. Let's see. So this is one of the stock materials in the Autodesk material library. If you do look through this, you will see a combination of linear and non-linear materials. So you'll see all kinds of things like metals and glass and plastic materials like this one. So we'll get into how we, I guess, access the non-linear properties of this material in a little bit. But for now, we just want to look at how is this going to behave with the linear static analysis? What is it going to look like? And is that good enough in some cases? Is it not? So that's what we want to look at. So notice I have a mesh going here already. It's a pretty fine mesh. So I'm not going to bother changing that. But the way this problem is set up is very simple. That keeps happening. I'm just going to fix the bottom face of this. So try to simulate that action there. Just fix the bottom face, excuse me, of that. And we have a load that's being applied on that face. So load, we're trying to simulate the action of something actually hitting the guard as this hedge trimmer is in operation. So load is a fairly small load of, let's say, oops, that should be in the X direction. The negative X direction, 75 pounds, really small load. And if you cannot actually see the load display, then you can change those options there. You can see that display there. So simple enough setup. I'm going to run the problem. And we want to look at where we see areas of high stresses, where we see these stress peaks, and if that's how that's actually going to affect the behavior of the system. So this should solve and finish solving. There we go. Now, safety factor wise, we see that well, the system's safe. Let me just make it a little more visible. And let's actually look at the stresses. Right, so I want to look at the solid von Mises stresses. There we go. So our highest stress is 6,000 odd psi. If you look at this, just the location of the stresses, the highest stresses in that region at that area of contact. So that, first of all, is an indication that we should be running nonlinear analysis, because you have a sharp corner contacting with a curved surface. That's never a good recipe for if you're looking for a safe design, you don't typically want to be doing that. And if you are doing that, if that is the nature of the design, then you should be running a nonlinear analysis. So the idea of this is to look at where these stress peaks are and see what that looks like with nonlinear. Let's try and correlate that. So if I were to set up nonlinear analysis, I'm going to edit my analysis type, change that to nonlinear static. Now, if you go into the options here, you actually have a checkbox here with a drop-down menu here, which allows you to turn on or turn off large displacement. And again, this is just a prediction. I know sometimes you're not actually going to be able to tell beforehand whether the displacement is going to be large or small. So the reason it asks you for this information is because the methodology it employs to calculate the stresses and the displacements is going to vary slightly depending on whether you choose on or off. But by default, it's okay to leave this on. It's not going to throw off your results. But if you do turn it off, then keep in mind that there's an entire section, that potentially there's an entire set of behavior, I guess, that you're simply not going to be able to see. So we'll just leave this on. It is on by default. A couple of other things you need to keep in mind for nonlinear analyses is you actually have to access the nonlinear properties of the material. So if you edit the material properties and you look at the analysis specific data, you hit this nonlinear button, then you'll see that you have different kinds of behavior. So at the moment, nonlinear is not active. Now we have nonlinear elastic, non-elastoplastic, and pure plastic. PCABS, we're going to treat this as a pure plastic material. And it does give you some information. It populates the strain, and it gives you the yield stresses and the yield strains. But the idea is to is to come up with a plot that looks like this. So we're going to approximate what the next value, the next point in that is going to look like. So I'm going to say 0.1, 8,000. And that's close enough for a plot. It's not a smooth plot, but it's close enough. So now you notice it says nonlinear on, and that's how you know you've accessed those properties. One other thing that you have to make sure you do, maybe not make sure that you do, but one other thing that you might want to keep in mind is the nonlinear setup itself. The problem will run even if this is completely empty, if this is blank default. But if you did want to have a little more control over it, you can change this to, say, 10 increments or 20 increments, depending on the interval that you want to keep seeing the results. And you also have this intermediate output. Keep in mind, this may slow down your computer a little bit if you turn it on or turn on all. That's because it tries. This is just an option whether or not to show you the results as it's solving the problem is still being solved. So you can keep this off, you can keep this on, depending on how impatient you are to look at the results. Personally, I like to turn it on, just so if the behavior doesn't make sense, I don't have to go all the way in. I don't have to wait for the solution to solve, to finish. I can just stop it midway and go back and change my inputs. So this does take a little while to run. So I do have that set up already. I do have the results set up already. So we see some interesting results here. First of all, just the basic stress value itself. And again, I haven't changed the mesh on this. I haven't changed anything else on this except that this has gone from a linear static to a nonlinear problem. The stress on this is actually increased, which is fine. But notice where the stress concentration is. Notice where the hotspots are. That now is at these edges, at the outside edge of this. Let me animate the results. Just give this a second. We'll see that there's not just linear bending of this, almost as a cantilever beam, right? That's what the previous one was being treated as. It was fixed on one end, the other end was just bending back and forth. So it was being treated essentially as a plastic cantilever. Hang on. Yeah, the animation tool is can be a little difficult to use. But you'll notice that this is not actually being treated just as a cantilever. This now bends like a cantilever, but then this portion also bends inwards, which is why we see this extra stress here, and that's the actual region where you see hotspots. These areas of contacts, sure, those are still bad. That's a potential design issue that may need to be fixed. Right, but if I probe those results, now that's still not, it's not that bad. It's better than it was previously. It's better than the previous linear static calculations. And it's not even the most highly stressed portion of this design. So that was just a quick linear versus nonlinear comparison and what that difference actually looks like and how significant it can be. So if you're approximating your problems that should be nonlinear, if you're approximating them to linear, and you're making design decisions off of those results, then you're probably still over designing, or you're probably still, you have some errors there in your design, that something that can be fixed. So this is just one small piece of nonlinearity. Again, this was the most obvious piece, which was the material itself. But I guess the takeaway from this would be that it's worth keeping in mind, at least in the back of your head, that potentially your design may function, that potentially your design may perform more realistically if you ran a nonlinear analysis to check. So, any questions based on this so far?
All right, thanks for that, Nikhil. So, as we mentioned, there's a lot of different scenarios where nonlinear will come into play. So, Nikhil wanted to make sure he showed some examples. I especially like that he started off with linear, because the idea is sometimes you might not realize that you need to go to nonlinear until you start to see some of the results and knowing you have to go there. Some cases it might be straightforward, right, and you go straight there, but not always. So, right now I know we're scratching the surface too, and there's probably a whole lot more questions. There's a lot of different scenarios we could have gone over too, but wanted to get started somewhere, right? So really, I think we're ready to go ahead and start the questions. Let's take a look at what we got. Where to download the slides? Nigel, do we usually post these somewhere?
So the slides generally don't get posted, but the recording of this does. So for those of you who are watching the recording, hello. And yeah, these get posted on our YouTube channel pretty shortly after the webinar is over. Just a couple of edits have to be made. And then it gets posted up on there. So you can always find this information again. If, say, for example, you missed a couple of minutes of it, you'll find it on our YouTube channel. That's going to be youtube.com/KETIV Technologies. Or if you just search KETIV AVA on YouTube, you'll be able to find all of it. There's over 200 videos there now, just AVAs, in addition to a couple hundred other videos just in general. So definitely take a look if you need to readdress this in the future.
All right. So we have a specific question here on part of the setup there, Nikhil.
Mm-hmm.
Quentin is asking, why would you constrain this in the fashion shown since it is retained by a screw and guided by the body?
So this was a quick approximation of how this behaves, right? Essentially, sure, it is constrained using the screw down there, and that's how we should be doing it. But it is a good enough approximation if we're just testing the strength of this, that we don't have to really take into consideration the screw and the body itself. If we're just testing the strength of the actual guard.
Yeah, and I'll just add something to that too. Is like generally when we're looking at things like this, we want to get an idea of how it's behaving and a general approximation of what the actual object is seeing. So you can simplify the problem a lot in that case. And sometimes when you do simulations like this, you want to be simplifying some parts, some bodies, because sometimes the geometry doesn't lend itself well to the simulation, or it'll overcomplicate things, especially on the mesh side of things. So just the simplification of the problem, pretty much.
Okay, and we have something here to clarify. I think if there's something you said earlier, Nikhil.
Mm-hmm.
Josh is asking, did you say you would want to do a nonlinear analysis anytime a curved surface meets a point, or is it anytime a curved surface meets a straight line?
Well, it's anytime you have curved surfaces meeting a point, meeting a straight line, anything that may lend itself to significant stress concentration by contact. I don't mean, little holes and notches, but I mean significant stress concentration by contact. Maybe you want to look at a nonlinear analysis.
Okay.
And again, that's regardless of how it's modeled, whether it's an assembly, whether it's one composite part, you're still going to see those stress peaks. So yeah, just maybe consider a nonlinear analysis and try and see what that does, because the behavior at those stress concentration regions is definitely not linear.
Okay. And then something from Sasho here. We're wondering if this data set that we use, does it happen to be in one of the tutorials or sample files that Autodesk has? Or is there something that you would recommend?
I'm not exactly sure. It may be online on one of their online downloadable data sets. Mm-hmm. I'm not quite sure.
Okay.
But
So we'll look into that
we'll
then.
look into that.
Sasha, we'll email you directly there if we find this exact one is available for the public or not. I know there's definitely a lot of examples, but maybe Nikhil, we can take a look at if there's an example that we can send directly to him, to Sasha. All right. Jerry is asking if there's any disadvantage to just always run nonlinear instead of linear. The only thing I can think of is time, because nonlinear will take a little bit longer. Anything else you'd like to add to that, Nikhil?
And complexity as well. Nonlinear does add a ton of complexity to the problem itself. So even if you do have contacts, right? There may be times when it's just easier to approximate as those contacts as a linear problem. So again, none of the things that we talked about today are blanket statements or blanket rules. They're all, with FEA, with simulation, there's always a rule, and you can find an exception for pretty much every problem to the rule. So I think we should consider these as guidelines more than something that we have to be following at all times.
Just like even when you said about the curved surface meeting to a line or a point, these are just things to look out for, right?
Yeah. So yeah, nonlinear can get a little complex. For example, just to look at that, right? You just in this nonlinear setup, we didn't actually change anything, but if you went in here, you can change each of these values, and it'll give you different results. And some of them are fine by default. Some of them are very problem specific. Like for example, sometimes you'll have your stiffness updating or not updating, depending on how that happens. How do you want your convergence to happen? So there's a lot going on here. There's a lot that goes in here. So it may or may not be advisable to always run a nonlinear analysis, especially considering how long it takes. For reference, the linear static on this, as we saw, took about 10-15 seconds. The nonlinear took about, I think, 10 minutes or so. So it's the same problem, the same mesh, but just for reference, that's how much of a time difference there is in actually running it.
Yeah. I saw Sasha made an extra comment there. We'll definitely make sure to look out for an example like the one you're mentioning there with multi-bodies as well. Because you can do, by the way, little side comment, you can use multi-bodies in here too, right? It doesn't have to be a full assembly necessarily.
Right. It doesn't have to be a full assembly.
Yale is asking why it results with high stress concentration in the middle of the edge.
Because so the reason for that is the bending that we see. It doesn't just bend from here to here. It bends from here to here, and these edges bend inwards. So because they bend inwards, we see stresses on those. Let me see if I can. Yeah. Yeah, this takes a little while to open that.
Yeah, just based on how it's actually loaded and how it's how it's structurally attached. Makes sense. It's like free to move at the top and it's fixed at the bottom, causing this thing to bend, and then you've got stress concentrations there on the edge because that's the curved surface. So yeah.
Right, so you also have this edge that bends inwards. Notice the shape of that changing. Right, so the bending, earlier you saw the bending was completely straight. Now it's not completely. It wasn't bending it was bending together earlier. Now it's not. So that's why you have that stress concentration there.
Okay. Yeah, you'll have some continuing questions here that kind of talks more to this high stress at the edge and maybe thickness changes and stuff like that. I think it might be better to have a side conversation with you, Yale, and we can kind of talk about those points a little bit further and make sure we fully understand your questioning and be able to interact with you a little bit more. All right, we have another question here. Where did it go? Got more questions coming in.
The one from 1028.
There it is. How did you determine your additional plot point on the nonlinear stress strain plot?
Oh, so that would be, where's that? So the points that the system's going to, the program is going to generate for you are this one, which is 0, 0, and that one right there. So the next point that you want is essentially, you want a plateau there. So the strain, which is the x-axis, you just want that to be a really high value. So I just increased it by an entire order of magnitude. And you want the stress to be pretty much the same. So I slightly increase the stress because this is, it's not exactly linear from here. So it's simply an approximation. Now, if you had a number of points, if you had actual test data, then you can put in all of those points and you should see a curve like this when you look at the XY plot. But now this is just to sort of get the shape of the curve.
Yeah, it's from actual material properties. It's not just like some arbitrary number Nikhil came up with, right? So you can look these things up if you want to. I think MacMatWeb probably has this information.
Yeah, exactly. Now this one might have to make a quick guess. Excuse me, a quick guess. But Michael, I think it's Michael, is asking, there was a field that you said could be left blank that was related to the number of cycles, I think, that the nonlinear analysis runs. How does this influence the accuracy of the results when you increase this number? Do you recall when you went to that dialog box?
This one, the number of increments.
Iterations. So, increments, sorry.
How will this influence the accuracy? It may or may not. So regardless of how many, actually no, it doesn't, right? If you do 10 increments for a problem that would normally take 100 increments to solve, it would essentially combine 10 sub increments into one, and you'll see the results a little later. So that's the only thing. You see results at the different, time steps, so to speak. So even if you did leave it blank, it's just going to go for as long as it takes. If you do specify a value, it'll take that many increments, but then it also has it solves based on sub increments.
Yeah, it'll still take the same number of iterations to solve.
It'll take the same number of iterations to solve it.
But the number of those iterations that are like shown, I guess.
The number of results that you see will be different, and that's the only thing. So for example, there's some things that you want to see results at every little instant for, where you're trying to look at a continuous set of results. So you want to have a really large number of increments, and that way you actually see the behavior from time 0 to time n. But if it's just looking at the final results, then it doesn't really make a difference. It doesn't affect the accuracy.
Thank you. All right, from Joseph, how does nonlinear affect model convergence? Does it?
Yes.
Okay.
A lot. So nonlinear and model convergence is a big that's an entire topic by itself. So there are different convergence criteria that you can sometimes choose in here. I think that's beyond the scope of this specific AVA.
Okay.
It's definitely something that we should talk about in the future.
Okay. Yeah, we'll start considering that for another Nastran In-CAD AVA.
For sure.
But for now, maybe if we can find some material, Joseph will definitely send it your way.
Yeah. So just keep in mind that if you do have issues with convergence, you can control it by selecting one of these. So if you're selecting work, for example, it's going to take care of displacement and load. If you don't care about the load, just select displacement, and it's going to try and ignore the other two relatively anyway. So on a high level, that's what you can do for controlling the convergence.
Okay. Sasha was asking, can you input multilinear instead of bilinear? Do you know what that would be in reference to exactly?
No.
Okay. We might need some little more clarification
Maybe
on
in
that, Sasha.
terms of maybe he's talking about the materials, but yeah, I think we need some clarification on that.
Okay. Yeah, material, he's saying.
Okay. No, so there's no multilinear material. That's not an option
Okay.
in NCAD.
How do you determine, there's another one from Steven here. I'm not sure if you could just add there was a quick answer for this, Nikhil, or if this will have to be for like a convergence AVA. But how do you determine what part of the model is failing to converge?
You'll
like
know.
a quick tip.
You'll see. You'll know. So when you're running the analysis, it actually shows you convergence of displacement work and load. So you'll actually see the one that's not converging. You'll be able to pretty clearly tell. So if that portion is not converging, then make sure that the program ignores that as much as possible and just it converges the ones that need to converge.
Got it. All right. I think this is the last question, if I'm not mistaken. Oh, sorry, two more. Would you recommend using nonlinear analysis when looking at high loads being applied over small areas?
Yes.
Okay.
Yes, because that's the very definition of buckling. So for sure, I'd look at nonlinear and do a buckling analysis as well. So buckling analysis will give you the eigenvalue, which is essentially a buckling load factor. So based on that, it's going to tell you if it's actually going to buckle or if it's just going to fail. And based on that, you can decide if it's linear or nonlinear.
Got it. And I believe this is the last question. Does the number of increments affect how the animation displays?
Yes. Yes. So the animation is going to display based on the number of increments. It's going to go increment by increment and not sub-increment by sub-increment. So the more the number of increments that you have, the more
smoother
the animation.
Yeah, exactly. And again, thanks everybody, and we'll see you next week.